So our next topic is on sound. So I will be able to understand sound. We're going to take notes from a video, perform or observe an experiment, and discuss with our peers. So the definition of sound. Sound is a longitudinal mechanical wave that travels through an elastic medium. So many things vibrate in air, producing a sound wave. So the sources of a sound, it goes through the air, and it hits our ear. So the example here is a tuning fork. So the famous question, is there sound in the forest when a tree falls? Sound is a physical disturbance in an elastic medium. Based on our definition, there is sound in the forest, whether a human is there to hear it or not. Because the medium there is now air. So sound requires a medium. The sound of a ringing bell diminishes as air leaves the jar. No sound exists without air molecules. Graphing a sound wave. The sinusoidal variation of pressure with distance is a useful way to represent a sound wave graphically. Note the wavelengths defined by the figure. So factors that determine the speed of sound. Longitudinal mechanical waves have a wave speed dependent on elasticity factors and density factors. So consider the following examples. A denser medium has greater inertia resulting in lower wave speeds. So a denser medium being here the steel rod. A medium that is more elastic springs back quicker and results in faster speeds. So water, which is more elastic and like air is very elastic, will bring you more speeds or greater speeds of sound. So sound waves in air are produced by the vibrations of a violin string. Characteristic frequencies are based on the length, mass, and tension of the wire. So vibrating air columns. Just as for a vibrating string, there are characteristic wavelengths and frequencies for longitudinal sound waves. Boundary conditions apply for pipes. So the open end of a pipe must be a displacement antinode A. The closed end of a pipe must be a displacement node N. So again, velocity and wave frequency, the period t is the time to move a distance of one wavelength. Therefore, the wave speed is equal to the wavelength over the period, which also brings us back to the velocity equals frequency times the wavelength. So an open pipe, possible waves, frequencies for open pipes, possible waves for a closed pipe, possible waves for a closed pipe as well. So what length of closed pipe is needed to resonate with a fundamental frequency of 256 Hz? What is the third harmonic? And assume that the velocity of sound is 340 meters per second. So we go with this equation. The frequency of n equals n times the velocity over 4 times L. We also have this equation, well, it's the same equation, I'm sorry. So the first harmonic is the 1 here. We put a 1 in for n, so we still have v, in which case the velocity would be 340. In here they have cross multiplied, so the F1 just changes places with the L. So I have 340 over the 4 times 256 Hz, which is the fundamental frequency, which gives us L, which is the length of the closed pipe, at 33.2 centimeters. The third harmonic occurs when n equals 5. So the third harmonic is basically 1280 Hz. So F of 5 equals 5 times the frequency. The frequency that we started with was 256. So that gives us the third harmonic. Okay, that's basically it. Probably really won't see that many problems on harmonics, but really the vocabulary is most important.